Picture a 5G network as a city with dozens of specialized departments. One manages your phone's mobility, another manages your data sessions, another watches over security. None of them work alone. Every second, they need to ask each other questions and pass along updates. So here's the real question this video answers. When one piece of the 5G core needs to tell another piece, hey, something just happened, how does that message actually get there safely and fast? That's not a small detail. It's the plumbing that makes 5G's flexibility possible. Older mobile networks used rigid, purpose-built links between boxes. 5G tore that up and replaced it with something that looks a lot more like the modern web. Network functions, the individual software components of the core, talk to each other using APIs, the same style of interface your phone uses to load a weather app or a map. We're going to walk through exactly how that conversation works. The language they speak, the addresses they use to find each other, how a message actually travels across the network, how two different operators talk securely, and a real example, a network function called the SMF, watching your data session and shouting, "Something changed," the moment it does. Let's start with the language itself. Every network function in the 5G core speaks HTTP/2. Yes, the same HTTP that powers your web browser, just a newer, faster version of it. Why does that matter? Think about old-style websites. Your browser opened a connection, waited for one file to fully download, then asked for the next one. Slow, one thing at a time. HTTP/2 throws that away. It gives you binary framing. Messages sent as compact, efficient chunks of binary data instead of bulky text, and bidirectional multiplexed streams, meaning dozens of requests and responses can travel over the very same connection at the same time, each with its own priority. For a 5G core juggling millions of subscribers, that's the difference between a single-lane road and a multi-lane highway. Underneath HTTP/2 sits a stack you can picture like layers of a sandwich. HTTP/2 on top, carrying the actual application messages, then TLS below it for encryption, then TCP for reliable delivery, then IP for addressing, and finally the physical link layer, L2, at the very bottom. And within that HTTP/2 conversation, network functions use familiar verbs to act on data. GET to read something, post to create something, put to update it, patch for a partial update, and delete to remove it. Same vocabulary the web already runs on, just repurposed to run a mobile network. Okay, network functions have a shared language, but before two strangers can talk, they need to know each other's address. That's what a URI does, a Uniform Resource Identifier, which is just a fancy name for the exact address of the thing I want to talk to. Every API in the 5G core follows the same four-part address format. API root, then API name, then API version, then API resources. Think of it like a postal address: country, city, street, house number, each part narrowing down exactly where the message needs to land. Here's a real one: http://10.0.0.1/nsmf-event-exposure/v1/pdu-sessions. Break it down with me. 10.0.0.1 is the API root, literally the network address of the server hosting the service. NSMF-event-exposure is the API name. It tells you which service you're calling. In this case, the Session Management Event Exposure Service we'll dig into shortly. V1 is the version, so both sides agree on which rules of the conversation they're using. And PDU-sessions is the specific resource, the actual data session you care about. Get this format right, and any network function anywhere in the core knows exactly how to find and ask for exactly what it needs. So a network function knows the address it wants to reach. Now, how does the actual message get there? This follows standard HTTP routing rules, the same ones the broader internet uses, laid out in a document called RFC 7230. Here's the walkthrough. First, the client, the network function sending the request, looks at the target URI and checks its own local cache. If it already has a fresh copy of the answer sitting nearby, it just uses that. No need to send anything at all. If not, it checks. Is there a proxy configured for this target? A proxy here works like a regional sorting center for your mail. Instead of you personally delivering a letter across the country, you hand it to a hub that knows the fastest way to route it onward. If a proxy is being used, the client connects to that proxy, and the proxy reads a special field called the authority pseudo header, basically a shipping label naming the final destination server, to figure out where to forward the message next. If the proxy itself doesn't have the answer cached either, it forwards the request onward, possibly through another proxy. And if there's no proxy at all for this target, the client skips the middleman entirely and connects straight to the authority server, the direct delivery option, like hand delivering a letter yourself. Once the answer comes back, the response simply retraces that exact same chain of connections back to the original client. Same road, opposite direction. That routing works fine inside one operator's network. But what happens when the message needs to leave the country, so to speak, when it has to cross from one mobile operator's network into another? That's called inter-PLMN signaling. PLMN just means Public Land Mobile Network in plain terms, one operator's entire mobile network. And you cannot let two different operators' internal network functions just talk to each other directly. That would be like handing a stranger the keys to your house. Instead, 5G places a dedicated security guard at the border, the Security Edge Protection Proxy, or SEPP. Think of it as a customs checkpoint combined with a secure courier service. Here's exactly how it works. If the client realizes the authority it needs to reach isn't inside its own network, it hands the message to its own SEPP instead. That initiating SEPP then sends what's called an N32F HTTP request. Its target URI is set not to the final destination, but to the peer SEPP on the other operator's side. And critically, the payload of that message contains the entire original HTTP message, rewritten into JSON objects, essentially wrapped up like a sealed, tamper-evident envelope for the trip across. The peer SEPP on the receiving side unwraps it, reconstructing the original HTTP message, and only then forwards it onward to the actual authority server that should handle it. Two operators, zero direct trust, and the message still arrives intact. Now let's ground all of this with one concrete working example. Meet the SMF, the Session Management Function. Its job is to manage your PDU sessions, which is just the technical term for your actual data connection, the thing that lets your phone send and receive internet traffic in the first place. Think of the SMF as a traffic controller sitting over every active data session in the network, watching each one, aware the moment anything changes. But a traffic controller that only watches and says nothing isn't useful. Other parts of the network need to know when something happens to your session too. So the SMF exposes a service called NSMF Event Exposure. A mouthful, but the idea is simple. It's a notification system. Other network functions can register interest, subscribe, with the SMF, and the SMF will actively push updates to them the moment something worth knowing about occurs. Who actually subscribes to these updates? Three main consumers. The Network Exposure Function, NEF, which can pass session information out to trusted third-party applications. The Access and Mobility Management Function, AMF, which needs to stay in sync with your session as you move around the network. And the Application Function, AF, an outside service, like a video app, that talks to the 3GPP core network to get context about your session in order to serve you better. Each one taps into the exact same NSMF event exposure service to stay informed. So what exactly can these network functions subscribe to? Think of it like setting up traffic alerts for a specific stretch of highway. You don't want every alert in the city, just the ones relevant to your route. The SMF can notify subscribers about 5 kinds of events on a PDU session. A user plane path change, meaning the actual data route your traffic takes through the network shifted. Perhaps a session anchor point was added or removed. An access type change, say your phone hopped from Wi-Fi access onto cellular or vice versa. A PLMN change, you roamed from one operator's network onto another's. A PDU session release, your data session ended entirely. And a UEIP address or prefix change, your phone's actual network address changed underneath you. Here's the part that matters. Getting these events wired up isn't automatic. It works through 3 precise operations, and the API table spells them out with exact HTTP methods. To create a brand new subscription, a consumer sends a post to the subscription's resource. To check on an existing one, it sends a GET to that specific subscription's ID. To modify a subscription, it sends a PUT, and to cancel it entirely, a delete. 4 clean, deliberate actions: create, read, update, delete, mapped directly onto the same HTTP verbs we met earlier. Now doing real work managing who gets told what. Let's make this concrete with a single walkthrough, start to finish. Imagine you're on a train, streaming video, and you cross from one cell tower's coverage into a completely different part of the network, enough that your data session's actual path through the core changes. Here's the chain of events, step by step. Before any of this happens, the application function behind your video app already sent a subscribe request to the SMF, a post to the subscriptions resource, asking to be told about exactly this kind of event, a user plane path change. That subscription is sitting there, waiting, like a standing order at a newsstand. Now, the moment your session's path actually shifts, the SMF doesn't wait for anyone to ask, did anything happen? It immediately triggers a notify. That notify travels as an HTTP2 message. Remember, fast, multiplexed, prioritized, addressed using the exact URI format we built earlier, pointing straight at the application function's endpoint. If that application function happens to be sitting inside the same operator's network, the message takes the direct or proxied route we walked through. Check the cache, find a proxy if one applies, or connect straight to the authority server. But suppose that application function is actually run by a different company, sitting behind a different operator entirely. Then the message doesn't go directly at all. It's handed to the SEPP, wrapped up securely, carried across the operator boundary, and unwrapped by the peer SEPP on the other side before it's delivered. Either way, within milliseconds, the application function knows your path changed, all without a single manual check, all because one subscription and one well-addressed HTTP2 message did the entire job. So a subscription exists. Now what actually happens when the event fires? This is the payoff of everything we've covered. The moment a subscribed event occurs, say a PDU session gets released, the SMF itself initiates the notify operation. It doesn't wait to be asked. It proactively reports the event straight to every NF service consumer that subscribed to it. That message rides on HTTP2, addressed using the exact URI format we walked through, routed through proxies or directly as we described. And if the subscriber happens to sit in a different operator's network, securely escorted across through a SEPP, just like we saw. Every single piece of this lecture working together in one notification. And consumers aren't locked in forever either. At any point, using that same unsubscribe operation, an NF can withdraw and stop receiving updates it no longer needs. Let's zoom out. We started with a simple problem. How do dozens of independent software components inside a 5G core actually coordinate with each other? And the answer turned out to be an elegant, layered system. HTTP2 as the shared high-speed language, URIs as precise addresses, standard routing to find the path, SEPP as the secure border crossing between operators, and services like NSMF event exposure as the nervous system that lets one function instantly alert others the moment something changes. That's not just how the SMF talks, that's the blueprint for how the entire 5G core stays in sync.